So just a point about today's key idea, we're really only going to introduce one equation, which is why we're not going to have to spend very much time doing anything except solving examples. The examples that I'm going to solve today, the code will be included on the TED site. So all of the screencasts are posted on YouTube, and there are links to them on TritonEd. I can't post the code anywhere other than TritonEd, so that's why each lecture is its own folder. So the code that I'm developing today, I'm going to post exactly that code in the lecture folder sometime after class. There's not much that you can do while I'm writing the code other than to try to pay attention to what I'm doing in the code. I will explain what I'm doing each step of the way, unless you have your laptop with you and you want to play along. Yeah?
Are you going to post a practice answer by any chance?
No. But I am going to discuss a particular type of question that shows up on the midterm in the next slide. But no, I don't have any practice exams. Yeah?
How many questions are the midterm?
There's only 2 questions, but they have subparts. So, Benny?
And no code, right? So there's no MATLAB.
There's no MATLAB on this exam, correct. Because we're not really getting into that core of MATLAB until now, where we really needed to solve the problem. So eventually we will get to this equation, which is just our expression for what happens if the system is not adiabatic. Remember we saw before that if a system is adiabatic, then Q is 0. Actually, there should be a dot on there. If it's not adiabatic, we only deal with one type of system where it's not adiabatic, and we'll see what this equation means when we get to it. So just a quick overview of a type of question that shows up on the exams. And it's not just in this class, it comes up in several of our classes. And just in case you've never seen a question like this, I want you to know what we mean when we say a particular phrase. So this is an example of a typical question that we might have, which is to write an expression for something in terms of at most certain variables. All this means is that your answer should include only numbers and those variables. Most often we use this because we're trying to keep the expression simple, right? We're trying not to make you solve something in a way that's quite difficult. We're trying to get some understanding of whether or not you know the general expression that we're searching for, right? So if I have x sub a in terms of at most the variables n sub a and n sub a not, an acceptable solution for this would be something like x sub a is equal to the moles of A initial minus the moles of A final over the moles of A initial. Right? That would be fine. Don't overthink some of these problems where I say do them in at most these variables and you wind up with a single line equation. That's entirely possible on these sorts of equations. An alternate that would also be acceptable here, remember I said it's those variables and any numbers that you think are relevant. You could also have 1 minus n sub a over n sub a naught. Right? Both of those are fine. So this is just a typical type of question that shows up on our exams. I know it shows up on the fluid mechanics exams a lot, where we ask for an expression in terms of at most certain variables. If you have a variable that shows up in your equation that's not part of that list, then you need to get rid of it somehow. Simplify it, substitute another expression for it. But very often we're asking for fairly straightforward expressions just to make sure that you know what the expressions are. So don't kill yourself if you see one of these trying to get rid of all of the terms. Any questions on something like that? The key phrase here is that at most the variables such and such. Just make sure those variables and numbers are the only things that show up in your answer. Cool beans? Okay, cool beans. So we will eventually get to that Q expression for non-adiabatic expression or non-adiabatic systems, but we're going to work on solving that example problem that we got to barely at the end of last class. I had passed out all the little handouts that had the little problem statement on it, so we're going to work on solving that. Just to refresh your memory, the 2 equations that we have to solve for the energy and material balances we saw looked something like the rate of change of temperature with time was our enthalpy term at some, usually I will give you an enthalpy at some reaction temperature, or I'll just tell you it's constant. If it's not constant, then we have to adjust it for temperature this way. delta Cp minus T minus Tr, where Tr, oh, those are supposed to be the same Rs. I don't want to confuse you there. R is just whatever temperature I gave you the enthalpy of reaction at. There's no universally agreed upon R. It was that term and then times R sub A times the volume of the reactor. And then we saw after a little bit of playing around, we could get the numerator to, or sorry, the denominator to look something like the moles of A times the sum of all of the theta i's times Cpi plus delta Cp times X sub A. Notice here that this V is constant. Right, so if that V is constant, that means, excuse me, we can express all of those concentration terms in the simple form. We don't have to use the big complex form that we saw before because we can actually hold volume constant now that we're allowing temperature to fluctuate. And so that was our energy balance, and then our material balance for A looked like the change in conversion with respect to time was just minus R sub A over NA naught times V. Each of these, remember, have to have some sort of initial condition. So initially, the conversion of A is almost always 0. And the temperature, which I can't add up there, the temperature at some time 0 is some initial temperature that we abbreviate as T naught. Every time we solve a differential equation, in order to solve it, we have to know where to start. And those are called our initial conditions. So we're going to use these two equations to solve the example that I gave in the handout. I have the handout here in front of me. The reason I gave you the handout is so I don't have to write it all here. So I'm not going to write it all here. But I'll go through more or less each step of it as I'm solving it in MATLAB. Unfortunately, I can't record this on the screencast, as I mentioned before. So you'll just have to pay attention because I'm going to stop the screencast right now. So we're done with that code example.
Professor sideways.
Oh no. Let's try this. When in doubt, turn it off and turn it back on again. Big money, no whammy. All right. So if we have something like heat transfer inside of our system, an adiabatic system had Q is 0. A system that has heat transfer has Q is not 0. And the way that we deal with energy is through this expression that I wrote a minute ago, which is Q is equal to UA times T minus TA. What are each of those parameters? If we want to heat up or cool down a solution, we usually have two ways to do it. I'm going to use liquid as an example because that's an easy one. One way is to pump cold water in through a tube, put spirals of that tube inside there, and just circulate water through. So they don't interact, right? They're not touching. If I were to zoom in on this structure, the tube itself would look something like this. And let's say, for example, you were trying to cool it down because this was an exothermic reaction. You would have, for example, cold water inside and hot reactant on the outside. And that tube is usually copper or something like that. And so you would have heat transfer from the hot liquid into the cold liquid. The area that we're talking about, A, so this term A here, refers to this surface area. Right? The tube is wrapped up and coiled around in there. Whatever the surface area is of that tube that's wrapped up and coiled around in there is the area we're interested in for that A. Typically, you will just be given that area as some number of cubic meters. The temperature that we have here, this temperature, is the temperature of the outside fluid. right? That's the same T that we get in our energy balance. It's the same one. So that, if you're writing a differential equation for it, is just going to be the letter T. The T sub A that we have here, oops, why did I erase that? This T sub A is the temperature of the fluid that's running through there. We've made an assumption here, which is that TA is constant, which is strictly speaking not true. Right? If I add energy to a fluid, it's probably going to increase in temperature, which means whatever the inlet temperature is, TA over here, is probably not going to be the same as the outlet temperature over here, right? There's TA going in this way, it spirals around and comes out over here. But we're going to make the assumption that these two are equal, right? The inlet and the outlet. It's not a bad assumption if you crank up the mass flow rate of that coolant. If you put lots and lots and lots of coolant through there, the temperature change in the coolant will be fairly small. And so that constant TA is not a particularly bad assumption. U, this parameter U up here, U is called the overall heat transfer coefficient, which is another number that we essentially have to give to you at this point. When you take your heat transfer class, you will learn how we either calculate U or generally we will look it up from correlations. But U is a number that we have to give to you. If you put this inside of our energy balance, because of the way that we have made assumptions about Q, did we say that Q going into the system is positive or negative?
Positive.
Positive, right? Generally, this Q is coming out of the system. The way that we've structured this, where we say T minus TA, that is describing energy that is coming out of our control volume and entering into the coolant. Therefore, if we write it in this particular form, we have to include a negative sign for this particular Q. So I'm going to put that out front like this. And technically, again, this should have a dot on it. We don't talk about the dots very much, but the dots are there. Right, so there's not a lot of new information here. The U, the A, and the TA are pretty much parameters that I have to give you. Or I might ask you to solve for one of them, right? Run the simulation over and over again until you figure out what an appropriate value of U or TA is, or something like that. There is another type of reactor called a jacketed reactor. So instead of directly submerging the coils in the fluid, that might not be a good idea if the fluid is particularly corrosive and we can't find any materials to do that. Maybe we have to line the whole thing in Teflon, which would be a problem. We can also jacket the reactor with the fluid, which we generally sketch like this. So there would be cold fluid coming in here, or hot. We can make things hot or cold. And it comes out the other side. None of the variations in the equation, though, change. The only thing that changes for this is what's the area that we're referring to. So the area in the coiled one is the surface of the coil. The area in the jacketed reactor is whatever this contact area is here. So whatever that contact area is, that's the new area for a jacketed reactor. So this one has a special name, which is a jacketed reactor. The one on the top doesn't really have a special name. It's just a reactor that's got a coil in it. So there's not really any new math here. It's just if you have a reactor that is cooled by something, that Q term is no longer zero, it's just this. But if you look at the structure of that code, that's basically like one more line in the code. It's not that hard to add in there.
If you have a jacketed reactor like that, does it have like something inside the circuit so it increases like
Yeah, usually there's a mixer inside there, inside both of them, like that.
Oh, you mean all the other ones?
Yeah, almost all reactors are typically agitated. Okay, I will see everybody here bright and early on Friday for the exam.